Okay. Are we all in? Good morning. Be on standby for the first few minutes. Andre, stand by. Okay. Okay. Sheila is here. Who's missing one? Still have one. Got that. Heimer, who is the missing one? Good morning, gents. Good morning. Hello.
Morning, Syed.
Yes, welcome back. How are you, Shirley?
I'm doing great, and you?
Good, good, good. You know who we are missing? Who is the third person? And they will be mute for 15 minutes. Okay. Let's see. 5 minutes. Stop.
Good morning.
Good morning. Hello.
Hello. Good morning,
How are you,
Mr. Said.
Kamal? How are you?
Fine. And you?
Good. Still alive? I was searching. I was searching for your voice the entire week, but I didn't hear anything from you.
Because it's a busy week for us. But I already downloaded the HISIS, but
Good.
I must update my computer. Maybe I think maybe tomorrow and at least Sunday I could
Okay.
install it and I call you again with the
Just text me on
instructions.
WhatsApp,
Okay.
and I will follow yours.
Okay.
Okay. Mr. Shirley, how are you?
Yeah, good morning. Yeah, I'm doing great.
Yes. What's your
Yeah,
plan today?
sorry.
What's your plan today?
Listen to you talk.
What are you going to explain to me for today?
Explain to you.
Yes. Tell me
Um,
what you remember from the last time.
Honestly, I've not had time to take a look because I wasn't. I didn't attend the last meeting. Ivar forwarded the presentation slides to me,
Yeah.
and I just took a couple of look at it. So I'm trying to do a lot of listening today, try to catch up and see if I could do a lot of what we did last week. Uh, I've not been able to download the Aspen Hysis yet, so
Yeah.
it's been a busy week for me too. So
No problem. With the
gonna be
promise
doing a
that
lot.
you're trying to catch up next time.
Yeah, sure, sure.
Perfect. Okay, just leave us with Kamal. Kamal, what question you have for me? Kamal? No? Houston? Kamal? Kamal. Why Kamal is... Mr. Kamal.
Yes, I am here.
Yes, welcome back. Tell me, what question you have for me from the last time?
I can hear you a little bit louder, please.
What?
Mr. Said, could you ask again, please?
I'm asking what kind of question do you have from the last time? What do you remember from
What
the
kind
last
of?
question you have?
I don't understand really.
I am assuming that you study, then you
Uh-huh.
have the record, then you have a lot of question for me.
Yeah.
Yeah,
Uh,
yeah. I can feel your smile from here.
yeah. Nope. I must collect my questions actually because it's a rough week. Last days, it's some kind of operation hard to us. I also want to ask if our subjects come to their actually limited process education.
Okay, which means I don't follow what you want.
Hmm?
I don't get what you want, what you say.
I
Yes.
don't really understand your question.
Do you have do you fully understand what we discussed last time? Do you have any clarification? You want to ask any question? Do you want to
Yeah,
explain anything from the last time? That's my
yes,
question.
yes, yes. Uh,
Yeah.
Not really for now, but I could arrange during this day, maybe for tomorrow from the WhatsApp, I think.
Okay. This will be good. No problem. We will survive with that. Okay. Let's start with today's plan. Okay. Let's start with there's this one. Okay. Mr. Shelley.
Absolutely, can hear you.
Yes, tell me, what do you know about hydraulic?
What do I know about what?
Hydraulic. Hydraulic.
Uh, um, when you talk about hydraulic head or hydraulic calculations or hydraulics, so movement of fluids or movement of liquid
Yes.
and how the pressure and height affects it.
And you, Kamal, what do you know about hydraulic?
Hydraulic is the it's, it's the fleet
What?
of which hydraulic is the fleet with them we operate something or maybe we're doing to work with it.
Yeah. What else?
It's I think it's a special kind of oil.
Okay. Let's start. Let's... Andrew, are you here? Andrew, I want to start. Okay. Hopefully he catches.
Yes, good morning, everyone. Yes, I'm here.
Yes, I miss your voice. Tell me, what do you know about hydraulic?
Hydraulic.
Yes.
It's a quite a broad subject.
Yes, tell me.
Hydraulic is utilizing liquid and fluid properties in different applications. Depending what we want, we can use properties of hydraulic hydraulics, and we need to understand how the hydraulic is behaving.
Exactly. It's good
But
definitions.
if you can ask more specific questions, probably it will help us.
No, it is not specific. It is just a general question to make introduction for today. Typically, I asking hydraulic. Hydraulic is the science of moving any fluids from one place to another place. That is the meaning of hydraulics. It is the science of moving one fluids, maybe it is gas, maybe it is liquid, water as firefighting equipment, maybe it is oil production as pipelines network. Okay, there's a lot of back noise there. Who have the noise?
I could close my microphone.
Okay. That's the meaning of hydraulic. The movement of fluids from one place to second place. That's what we are trying all the time to do. If we are transporting gas, we have a gas network. This kind of hydraulic we are facing. If we are transporting liquids like water, it is used in the firefighting network. If we are using oil, it is a pipeline network for oil gathering or production. Let's go a little bit back, a little bit deeper in that. Typically, if you have, here is the first wall, here is the second wall, here is the third wall, and here is your centralized processing facility, where you need to bring all the oil from here, all the oil from here, all the gas from this one. Typically, oil and gas are being transmitted to the CBF to get processing. We need to process our oil to remove any volatile components. We need to process our gas to remove all of the impurities. The first thing we have to do before processing is to be sure that this oil will reach all the way to the TBF. Right, Kamal? Does it make sense? Okay, right, Andrew? Does it make sense?
Yes.
Typically, if you have, let's say it is oil now, then we will be specific. Let's put all the three oils. Typically, if you have three oil wells, like what BP have, for example, in Gulf of Suez here in Egypt, then what they are doing, they make one line called trunk line, which accommodate all the three flow, all the three wells, and make a gathering for the three wells. That's what we are trying to do. Is that good? Is that satisfying the productions we have? Let's say this well is producing 500 barrel of oil. This second one is producing 300. This third one is producing 200. Typically, if you have a trunk line, by the end of the day, we are expecting, Kamal, we are expecting 1,000 barrel per day
Oil.
here, right?
Yes.
But in reality, we find 9.3 barrel per day.
I think we have some losses during the line, actually.
Yes. Why? We have losses.
Uh,
Is it
friction.
the line is leaking?
Nope. I think from a capacity loss from the vanes, valves, gates, maybe during the friction during the pipes, I guess.
Yes. This is a
Well,
good
it's a
one.
closed system, if I may answer you.
Yes, there's a closed system. So,
So where is the if you say you have unless there, I mean, are you on the assumption that there are no losses from
no,
wellhead
what I'm
or
saying
that?
what I'm saying is a real case happened with BB.
So is it the pressure drop and then you're losing a little bit of oil in the gases or
Yes. I want you to think loud.
prob-
Yes, you are going on the right way. Keep
or,
talking.
or probably you don't have good hydraulics from the lower production fields and so you expecting to get 200, 300, and 500 into the trunk line, but actually it's not getting into the trunk line.
Totally right. Let's go a little bit deeper first before we answer it. For example, this 500 barrel coming with a pressure of, let's say, 200 psi. This 300 is coming with a pressure of 150 psi. This 200 is coming with a pressure about 120 psi. This facility is operating at 50 psi. So typically this 200 will be more than enough to flow from well number 1 all the way till the CBF. Typically this 120 will be more than enough to move it all the way from here, going here, back here, going all the way to the CBF. Typically the 150, there's a background on that. There's a lot of noise, gents. Hello? Who,
Sorry,
who,
I am closing.
yeah, you are in the work, right?
Yeah, I'm on the office actually, but
Take your
we
time.
have a construction. Sorry, outside.
No, take your time. I can't feel you. You're trying to.
I closed the microphone.
No,
I only
no,
open it when we
no
are
problem, no
talking.
problem. Take your time. Then we have this oil, which is coming with 150, which is in a typical condition also it will flow all the way to the CBF, which is operating at 50 psi. But when we're using our flow meter here, we find it is 930. Why? Because this 500, 300, 200, when it was calculated according to a test which is being done on the Christmas tree. What do you mean, say? How does it work? Let's go a little bit down. Here is your reservoir for the oil. Then you're having all the way the production here. Then you're having your Christmas tree. When you have our production wing. What drive the oil from here all the way till it reaches the CBF there? Kamal, what
Yes.
what make the oil move from the reservoir here all the way down to the CBF?
The pressurizing power from the compressing unit.
We don't have a compressor units here. We have a reservoir pressure here.
Ah.
So the first thing we should learn about hydraulic, there must be high pressure at one side and lower pressure to the other side. This means if we have a pipeline, we should have B here to be bigger than B here,
The P1, yeah.
to have a delta B, to have a flow. So as long as the delta B increase, the flow increase. That's how it works in hydraulics. So if the delta B reduce, this means the flow will start to reduce. Is that right? Yes, that's right. This means we have a direct relation between the pressure and the flow. So let's go back again. If this is what we are trying to demonstrate. Here we have a delta B 200 and 150, so we have a delta B of 5150. Here we have a delta B of 100. Here we have a delta B of almost 70. So this big well, this high production well, will go first. Will go first. Why? Because it have a higher delta B, which will have a back pressure effect on the small wells, like the well number 3 and well number 2. What do you mean by back pressure? Because this well number 1 have a high delta B, it forces all the liquids at this tie-in points, please, to not enter here until my oil is passing first. So that's ended up by have some back pressure here for this well number 2 and well number 3, which lead to delta B reduce, delta B for the second, third well reduce, and accordingly the flow will drop. That's why we ended up by 930 at the CBF. That's why, yeah, Kamal, we are doing something called nodal analysis for this networks, oil networks, gas networks, any network in the university, in the universe. Sorry. Why? To make sure that we have the minimum delta
Pressure differences.
P and the minimum back pressure on the wells to get the maximum productivity of these wells. You got the gents? Hello? Houston?
Yeah, correct, sir.
Yeah, correct.
Any question about this? This is how we are going to build on the hydraulics.
Nope.
Okay. Based on that, you find another company like PB. What she did, what it did, she takes this, the lowest well, and well number 4, which have also 110 psi, and they make another separate line till it reaches the CBF. So when they have here 200 and this one was like 150 barrel, When they making another wall, another pipeline, they eliminate the back pressure from the biggest one on the low pressure wells, well number 3 and well number 4. That's how they are overcome the hydraulic or the differential pressure or the back pressure effect from the high pressure well on the low pressure wells. Based on that, when they making this another pipeline, the production restoring 100, 250, 350 here from this line, and from this line it was like 800 coming from 500 and 300, and 350 coming from the 200 and 150. That is how it works in the upstream facilities, in the network between the Christmas tree till you reaching your plant. That's happen if you are working in the upstream section. If you are working with the well department at your work company. Is that all? No, sir. We just start. Now you're working with the downstream people. Before I'm switching to the downstream, is it good for the upstream? Any question? Gents,
None from my side.
help me here. Anything is not
None
clear,
from my side.
stop me. Okay.
Okay.
From the downstream sections, now we have our plant. We have the production headers, the manifold, where all the wells are coming from the upstream. Then we have to ask ourselves, what kind of process we agreed from the last time? Let's say, we agreed that we are having sweetening unit in the feed stage. We agreed that we have a dehydration unit. Then we agreed we have a compression unit. Then we have a condensate stabilization unit. Then we have the dispatching lines. So let's start with you, Kamal. I will make from the manifold one line to enter the contactor, the first tower in this plant, which is the sweetening unit. Is that good, Gamal? Is that right?
Yes.
No, not right.
Why?
Why? Sweetening unit cannot operating only for gas, cannot operating for oil. So
No.
that is the basic default for us. If you are a process engineer, by blind, you don't see. The first equipment you have to put it after any manifold is a separator. Why, Kamal?
To
Because
separate gas from the liquid.
exactly, because gas processing units are different from oil processing units. So the first thing we are going to have is a three-phase separator to separate what? The gas from the condensate from the water. What is in between is the weir. We will see how we are going to size it in first day, don't worry. And now we have the gas. So let's back to hydraulic, not sizing the separator now. The line between the manifold and the separator command. What should be the size of that line? Should be like 10 inch, 12 inch, 14 inch, 36 inch, depend on what. Then we have a gas line from the separator going all the way till it go to the contactor, which is the first tower in our switching unit. The size of this gas line, how much it should be? Could be like 8 inch, 10 inch, 12 inch. Then we have the oil line, which is going to the condensate stabilization unit. This is another tower. What would be the size of this line? Is it 6 inch, 8 inch, 10 inch? Based on what? That is the hydraulic. That is kind of hydraulic we are doing between equipment, not equipment, between the skids, the steel structure which we have for the manifold, the steel structure but we have it for the separator. So let's take it line by line. Come on. Let's assume we are speaking about this line now. This line number 1. It is what is the fluid inside? It is a mixed phase. Right, come on. We have a gas, we have oil, we have a water. Right, sir? We
Yes,
have the
right.
pressure of this manifold. Let's say it will be like 50 psi as a P inlet for the pipe. Then we need P outlet, which will be, here is the beginning of the pipe. The beginning point is the manifold. The end point is the separator. Right, sir? Right, Kamal?
Yes. Yes. Right.
So, what we are trying to do now, what we are trying to solving now, is what will be the size of this diameter. To do what? To do what? To give you, Kamal, the minimum delta P. Focus on this word. The minimum differential pressure or pressure losses to deliver what? The full quantity from the manifold side till it reaches the separator side with the minimum delta B. So how we are going to try it, how we are going to solve it, we're proposing diameters. Let's say we'll put it 6 inch. 6 inch is very, very, very small diameter compared with the high flow which we have. So if you have a high flow and you have a small diameter, what will happen, Kamal? Do you have a water hose? Do you play with a water hose before? Kamal?
Yeah, I'm asleep.
Yes, when you was young, you play with a water hose, right?
Yeah.
When you squeezing the tip of the water hose, you find the
Yes.
water ejecting higher, right? You find the
Yeah.
velocity of the water increase, right?
Right.
That's
Actually, pressurizing the hose
exactly
during the limiting flow. Actually,
limiting flow and increasing the velocity.
pressure. Yeah.
And that, sir, is our first limitation, which is the erosion velocity. This is the first one. What is erosion velocity, Kamal? It is the velocity of gas or liquid water, liquid oil, which the fluid will start to eat the thickness, which start to make erosion effect
Region, the
on
inner
the
walls of the pipe
on
or hose.
yes, which will start, in another word, eat the thickness of the pipeline. You get it? Hello, sir. You got it?
Yeah.
That is our first limitation:
Yes.
erosion velocity.
Yes.
What else? What else we have?
Pressure.
Yes, I'm coming to you. Let me tell you. The erosion velocity is the first limit. What else we are trying to do, or trying to have as a limitation? Let's scroll it down. The second one will be the delta B across 100 meter. Most companies, all the GBSA's handbook, saying that the acceptable limit for a delta B to happen in a small pipe, its length 100 meter, the acceptable limit is 0.1 bar. 0.1 bar. So, if you, Kamal, now we're making this
1 bar or 0.1 bar?
0.1 bar for 100 meter,
Okay.
1 bar for 1 kilometer.
Okay.
We will see. Did you see the codes I shared with you last time? You will find different company standards. They're sharing this number only. We will come across it, don't worry. Here is the pipeline. So, when I need to select the diameter of this pipeline, I need to know the P in, P out. I need to understand the full length of that pipe, and based on try and error, I am starting with 6 inch. See how much erosion velocity I have, how much delta B I have. Write it, then run it again. 8 inch, 10 inch, 12 inch, until I reach figures which is being accepted. That will be the size of the pipeline. Andre, are you following me?
Yes.
Yeah, I got a question. So, what is
Yes.
the industry standard for the maximum erosional velocity that you're not supposed to exceed when you're doing these
Yes.
sighting calculations?
Totally right. API 14 CEH. All of these three APIs, you find the equation for calculating the erosion velocity in API C, appendix or paragraph C also. But all the three giving you the limitation for single phase flow, mixed phase flow. And the good part about HYSYS is that the equation is built in the HYSYS. Basically, as a rule of thumb, for a gas, you have a limit till 10 meter per second. For a liquid oil, you have a limit till 4 meter per second. For a water, you can reach 6 meter per second. That is the erosion velocity for different kinds of fluid. Does that answer your question, sir?
Yes, I.
Okay. Based on that, on the downstream, we are making something called hydraulic line list, which, if you're working with the EBC company now, what you're expecting line list. Let's go here. Line list from your piping engineer, and from this piping engineers will give you the starting point, the end point, and the pass, the length of the pass, and the fitting, and the valves.
And I think according to that, we are calculating to the delta P
Yes, which call isometrics.
isometrics.
Yes, which is, let me open one of these isometrics so you can. Yes, for example. Why it take a lot of time to open it? Okay. Ah, what happened? Okay. Ah, I hate that. Okay, keep going, please. What happened? Ah, come on. Yes. Okay, Jones. This is the kind of isometrics we are receiving from piping people. When we're receiving it, when we have it on the 6060 model review, 3D model review for our plant, where we can see the starting point, then it's going down, then it's going moving like 600 meters or 2.5 meters, then it's going up again, then it's going right, down, moving all the way. Then we have another manual valve here or control valve here, which will making a delta B for us. Then we have a tie-in here for another line, and here is Kamal. If you can see from the piping, the fitting, the flanges, it described to you how many accessories on this isometrics. Did you download the Excel sheets which I sent it to you? Gents, hello?
You see, no? Okay.
Did you download anything?
Yes.
Yeah. In the Excel sheet which I sent it to you,
Yes. Yes.
you will find. Let me open it. This Excel sheet is the Wally Parson Excel sheets. Why we are needed it? Because sometimes when I was traveling, I cannot find my HISA software. So I using the old traditional way to making hydraulic, single phase liquid hydraulic, single phase vapor hydraulic. That's the two ways which I can use it for doing hydraulics. Let me open one of them with you to get what I want to demonstrate. The good part about this Excel sheets is that you don't need to practice it. You don't need, because you have here a demonstration PDF calculation which showing to you how the Excel sheet is work. This Excel sheet is from Wally Parson 2014. This is the updated one till the moment. We are going to release another version of this by the end of this year. So here are the basic assumptions. Here is what we did. Here is the initial source. It is piping, equipment, control valve. Then we have from to. Then we have a description. Then we have to say, yeah, Kamal, what is the outlet pressure? Then the temperature. Then how much flow rate. Then we have how much design margin we want for this line. Typically, you are going for hydraulic for 10-inch, the 10%. Sorry. Then we have to put the density and the correction of the density and the viscosity. Kamal, you love the white honey, right?
Yeah.
If you put it
I
in
hear you. I'm listening.
what?
I am listening to you.
The white honey, do you love it, right?
Yeah.
Okay. If you put some white honey in the refrigerator, what will happen?
No, I don't know.
What?
I don't understand your question actually. Your noise coming
Okay.
from the
If you have some honey on the cup
yeah.
in ambient room temperature, and this cup fall from your hand, the honey will flow on the ground, right?
No, because this differs from the water. It's
Yes, but by the end it will flow, right?
yeah.
But if you put this cup in the refrigerator for like say 1 hour, then you bring it up and you flip the cup, the honey will not fall, right?
Right.
That is the same. That's why you have a viscosity constant in the hydraulic equations. Why? Because typically, Kamal, when you have a pipeline here, the fluid is, when it passing through the pipeline, it have to make first fill here, which will be adherent to the inner diameter of the pipeline. Then we have another layers, then another layers, then the moving layers which will be in the center. This will be the layer which is moving. That's why, yeah, Kamal, when we have a very heavy oil, which will correspond to very high viscosity, we are using big pumps to start to dispatching this one. But but on other hands, Kamal, sometimes these big pumps cannot push the heavy oil. You know why?
No.
Because of the viscosity.
No.
The same concept. The viscosity is very, very, very hard, which require a massive pump to push it, which require a big load, a big power to push this liquid. So you will end it up by not find a pump in the market able to push that liquid. So what we can do, the only thing we can do is to reduce the viscosity. Why? Reducing the viscosity will reduce the friction forces, friction losses, which will make this oil can be pumped can be pumped in the truck lights. How we are going to reduce the viscosity, Kamal? By increasing the temperature. If you're increasing the temperature of the honey, which is coming out of the refrigerator, and you put this cup in the microwave for 30 seconds, the temperature of the honey will raise again, and it will restore its fluid motion, its motion. It will be able to be a liquid again, not semi-solidified. This kind of things we are doing in hydraulic. Sometimes when you're running the hydraulics for the network we are starting in the beginning, it's little back here. You remember this example when we speak about the oil? Sometimes the pressure in the oil's head or reservoir is not enough to pump all this way down to until you reach your CBF. So what you are doing, you can use a heater at the beginning of the pipeline to heat it up the oil to a temperature like 80-70 Celsius to make the viscosity very low and make the oil pumpable in the pipeline till it reaches the CBF. Does it make sense? Hello?
Yes.
Yes, tell me. Who have a question? Andre, Sheila, are you good?
Yeah, I'm good from this side.
Okay.
Yep.
That's what we are doing in the midstream. We receive in the downstream. We are using the arithmetics from the piping engineers. Then we have the inlet, the outlet, and we're making all this configuration. Why I'm not using the I'm not using the Excel sheet now, because I'm going to use the HISIS when we are doing one of the isometrics. Then you will have the velocity, the friction factors depend on the material itself. Then equivalent length, the total length of the pipeline. Then it will, by the end of the day, it will give you the pressure losses, which is acceptable, which is not acceptable. Okay, as you can see here, the pressure drop will be calculated for each 100 feet. Okay, gents. Then we have the total pressure drop across all the whole distance. This Excel sheets, please do not share it with anyone. Keep it at your laptops only. This will help you to make a verification for everything you can dream about it in oil and gas. Just let me scroll down with you. as you can see from the ventilation, pump sizing, separator sizing, tower sizing, hot oil expansion vessels, pressure safety valves, channel and tube heat exchangers, all the way down, all the most of the equipment, even the orifice sizing for the flow meters. Anyhow, let's go back to what we did.
So if I may ask, did you already send this?
Yes, on the links, the Google Drive link which I send it to you, you'll find a lot of calculation, a lot of philosophies.
The one that has Excel sheets?
The what?
Is it the one that has Excel sheets on it?
Yes.
The one that has Excel sheets on it.
You can see my screen, right? Here's all these Google Drives. EVT standard, different standards to compare, PLP courses Excel sheets. Did you get it?
I don't think I got the process Excel sheets.
Why?
Let me check.
Here, sir. Just use the last
Yeah,
link. You'll find it.
yeah, I got it.
Person
Yeah, I got
process
it.
systems, design guidelines. Here, you'll find different guidelines from one persons. Then you have the calculation sheets, all the Excel sheets. This is a new one,
Oh,
and this is the old one. If I'm not mistaken. Yes. And then we have different readings if you want to read the original of these calculations. Okay?
okay.
That's how we are doing. That's how we are working on the midstream, on the downstream. The most important part for us. Yes, sir. Yes, tell me. Okay.
Yeah, I got it. Thanks.
You're welcome. So, the most important part from ourselves, Kamal, as a process engineer working in EPC company, doing hydraulic for the plant, is to make sure that we have the optimum pipe diameter for the gas side, the liquid side, water or condensate, according to the distance which is given by us from the piping engineer. The piping engineer and the man who put the layout of this plant will tell you the distance between the separator and the tower, and will tell you how much distance we have. Based on that, you're doing your hydraulic calculations. Okay? Okay? Come on.
Okay.
Perfect. That is the downstream people. Okay. And the last thing, Kamal, when we're doing this plant, one of the most important part we are doing for the plant is to calculate the overall delta P. How much delta P you have across the pipeline, the equipment, till you reach the export line from your plant. This is happen only for the gas side. Some clients require this delta B. If you're working with ADNOC or Aramco, you require this delta B across the whole plant. That is part from the downstream. Is it all? No, we still have a lot. For a downstream side, we still have a lot of things. Like what? Let's open some of the guidelines which shared with you. This is the one for the single line hydraulics. These are isometrics, I don't need it. Let's go back to our course material. Hydraulic. Okay. What is this? it is like 5 or 6 companies have different line sizing criteria. Line sizing criteria for Total, for Mustache, American company. They're telling you some velocities, some line sizing, velocity, and an acceptable back pressure in some section lines, discharge line. What does this mean, Kamal? How it's work? Let's explain it before they are doing it. Let's say we have a separator. Let's say we have a pump. Pumping the liquid out. Here, according to ABI, gents, we have till 4 meter per second acceptable velocity before we start the erosion section, our erosion phenomena, erosion mechanism. Companies like Total, like PP, like Shell. Let's start with Total. Total telling you, please don't go to this 4 meter per second. All the companies telling you don't go for 4 meter per second. For Total, it is acceptable to have 1.8 meter per second maximum in the bump section, and 5 meter per second in the bomb discharge. Okay, Andrew, I'm making my calculation before, and this line was 6 inch, but this line giving you a velocity of 7 meter per second. When I presented it to my client, the client will reject that, and it will tell you, please increase this size to be 8 inch. When you do it for the 8 inch, you find the velocity 4.5 meter per second. Then it is approved design. That's how it works. That's how it works between EBC and owner. The velocity here, the velocity here. That's for Total. For BB and BG, we're accepting this one till 2 meter per second. We're accepting this one till 6 meter per second. Depend on the company. As long as all these numbers are below the original velocity. Are below what? Original velocity. You got it, Jones?
Yeah, but what is the basis for the different erosional velocity, the velocity limits? Because it's as though there is no defined velocity for erosion to occur. Because I don't think BP wants erosion on their pipes, and neither does Shell. So if both of them are having a different velocity along the pipes, so what is their basis for making those decisions? Any ideas?
Let me put it this way. The restriction is the original velocity. We agree, right?
Yeah.
So we are not touching the 4 meter per second on this section line. Okay?
Yeah.
So you, as a PB, you decided to work 50% of the original velocity. I am like a Shell or Total. No, I decided to use it like 40% of the original velocity. Do you have any problem with that?
No, but I mean, what about the 5 meter per second on the discharge?
This is the point here. The 5 meter per second and 6 meter per second. When we're speaking about the original velocity here at the 4 meter per second, and we speak about the discharge here as a 5 or 6, is that acceptable? Tell me, sir.
Well, I mean, the pipes are. Let's assume the pipes are the same material.
Yes.
Yeah.
So,
So if they are the same material and they are subjected to the same, they are subjected to the velocities above the API standard, then
yes,
you'd expect velocity to occur. You expect erosion to occur on the one that is exceeding that standard.
exactly. So, by the end of the day, this two numbers is not accepted, right?
Yeah.
So, you have to increase the pipe diameter till you reach below the 4 meter per second. Right, sir?
Yep.
Thank you. This is what I want to hear. Did you get what he says, gents? Hello, Kamal?
Yeah, I'm listening.
When I was saying 6 inch, it was 7 meter per second. Then I jumped to 8, it was 4.5. And I was saying it is acceptable. No one stopped me. Telling me it's 4.5 is higher than the original velocity. How you accepted it? Then he stepped in, asking why we are accepting this for 4.5. Why we are accepting the 5 or the 6 meter per second? It is higher than the original velocity. Cannot be acceptable. If it is acceptable, this means this pipeline will have a pinholes after 1 year of operation, or maybe less than 1 year of operation, because erosion mechanism will happen and it will eat the metal thickness. So by the end of the day, gents, we have to be lower than the original velocity everywhere in the system, in the pump section and the pump discharge. Does it make sense, gents? Hello?
Could you explain again this side?
Okay. What is the original velocity? Tell me.
The velocity, the value beginning the erosion to the inner walls of the pipe section.
Okay. This means we need to be away from this
This,
mechanism,
yeah,
right?
yeah, we must avoid. Yeah,
So,
should avoid.
when we are doing hydraulic for the pump diameter suction line diameter or the pump discharge line diameter, we have to use the size of the pipe, the diameter of the pipe, to be to give us velocity will be lower than the original velocity. Right, sir?
Right.
That's what we are trying to say. Some companies operate at 50%, some companies operating at 40%, other company working at the like Technique, Italy, working for 30%. Depend on what, sir? Depend on the company and its consideration. But our biggest limit is the original velocity. When I was testing, most of you asking about the 5 and the 6, then I saying that 6 inch will give you 7 meter, 8 inch will giving you 4.5, and I was saying 8 inch is more than enough. Only him, Andrew, is stopping me, asking, telling me how you accepting the 4.5. It is higher than the original velocity. Based on that, we're choosing another higher diameter, which is the 10 inch, was giving us 3.8 meter per second. You get it, sir?
Yes.
You get how it works? It is try and error, sir, by the end of the day. You use 6 inch, then you calculate the velocity. Is it within the limit? Yes, it's acceptable. Not the limit, increasing the diameter. And keep increasing the diameter until you reach your limits. Until you reach your limits. Okay?
Okay.
Okay, who's typing on the keyboard? Okay. For example, here, who's typing on the keyboard, gents? Make your mute, please. Thank you. What?
Still typing.
Yeah. Okay. Let's see some sizing criteria for liquids. For example, pump section, you can reach till 1.8 if it is 20 inch. If it is less than 2 inch, you have to keep with 0.9. The pressure drop 2.3 bar per kilometer is acceptable per kilometer. Focus on this kilometer. And the maximum is 3.5, which means if we divided it by 1000 meter, so we are expecting 0.035 per meter. This is the pump section. Pump discharge can go till you reach 3 meter per second. Right, Andre? Andre?
Yes, I can see it, but I have a question. Where is this table from?
This one is which company is this? Let's see.
It's not API, right?
Not API. 1 minute. Let's open one company. Let's go for Parson. Come on. Let's open Mustache. Let's open ENI, Zoho, Plant. Configurations, okay. Course-2. This is ENI1, sir. You see, gents? You see the table? Take a minute to read the table and tell me, is it good or bad? Here is the pressure drop, here is the velocity, here is the equipment.
Yeah, you previously mentioned that for gases, erosional velocity limit is 10 meters per second.
Yes.
10 meters per second seems a bit slow for erosional velocity, and in this table, recommended velocity limit is, you can see it's
60 meters per second.
50 and 60 meters per second.
Yes, but it is a vacuum. Right? When we're speaking about original velocity, we're speaking about the transmission lines, the trunk lines. But for the equipment inside, which is working on a vacuum, which for the compressor, we have a difference because it is a turbulent flow. The API giving you the 10 meters per second. Let's open the API. 1 minute. Did you see the difference with your eyes? Where is it? 1 minute. Let me connect. Have a look here. Let me connect my external hard. to get the API. And here the liquid lines, as you can see, is the same. 1 minute until I connected my external hard to go for the API. See, 2.2 if it is higher than 20 inch. Why? Let's Google it. It's going 1 minute.
This looks like a liquid.
Yes. With the constancy which we are going to plot. Operations. Horizontal of some. Operations. Not here. Not until the external hard is opening. Here is the equation for the general pressure drop equations, which we consider the diameters and the Pn delta P for the pipeline. Then we have the length of the pipeline and the friction losses. Let's go for the velocity. Typical flow velocities, here is the 6. So for the compressor, yes, this is one for the compressor. Centrifugal or rotary pumps, you can reach till 6 feet per second, or 6 for 4.5 if you have a compressor with RPM, lower RPM. If you have a pump with lower RPM, 250 to 330, the centrifugal pump. No. What is that? Velocity equations. See. I don't find it strange. Anyone can see it? Tell me. Unusual velocity 23. Okay. Here is the original velocity equations which we are using, which embedded on the HICES. If you can see, the original velocity is being calculated by empirical constants, which is depending on the surface, divided by the square root of the gas liquid mixture velocity at flowing pressure and temperature. That's why one of the most important part to add it when we are calculating the original velocity is the pressure and temperature. And from HICES it will bring the density of the mixtures. C can be 100, can be 125 for intermediate surfaces, can go reach to 20. The density of the gas may be calculated in the following derivatives. I want to see where the 6 and 10 minimum velocity we can reach is. Here we are, sir. Minimum velocity, if possible, the minimum velocity in two-phase line should be about 10 feet per second. If we have a mixture phase, 10 feet per second, which is equal to almost 4 meters per second, to minimize sludge or separations. Let's see the other for the gas. Okay, I cannot find the one for the gas. I don't know why. Anyhow, gents, let's keep it back here. This is the one for the liquid, and I will bring the one for the gas. What's here? After the break, I will bring the one for the gas, gents. Okay? Hello? Hello?
Yes, thank you.
Thank you.
This is the massage one. If you can see the massage one, the American company, it has the same difference between 0.5 psi if you're going to pump section. If you're going for a pump charge, it's going to go to the 4 meter per second for the pressure drop, and the velocity is almost 15 feet per second. So the end result of what we are trying to say, or what we are trying to demonstrate here, different companies have different specs. The optimum for us is to avoid the original velocity. Original velocity is calculating according to the equations which we just see it here, which is embedded on the HICES software, and based on the equation the high-sense will calculate the velocity of the fluid, the original velocity, and we have to make sure that we are away from it. Okay, gents? Okay, gents? The man
Yeah.
who's typing on the keyboard, is it okay? Hello?
Okay.
Okay, the last thing before I take 5 minutes break or 10 minutes break. That is the type of flow regimes that we are seeing in our pipelines. It can be bubble, it can be plug flow, it can be straightforward, it can be wave, it can be slug flow, and please, please, please do your best to avoid this one. Annular flow. What's happening? Annual flow or dispersed or mist flow. This all kinds of flows which we are seeing typically from the wells till it reaches the facility. Then all these flows have to go for the straightforward one to make sure that we have a right calculations for every transmitter. When we come back after 10 minutes, we will speak about the firefighting, firefighting hydraulics. Then we will make simulation case for the hydraulics to close this part. Okay, gents?
Okay.
We have still the pump calculations, the pump data sheet. We are going to generate pump data sheet today. Okay? Okay? Hello?
Okay,
Okay.
Said. See you
Okay.
in chat.
Okay.
Yeah.
We will take a break for 10 minutes. I will make my coffee and come back. Okay?
Okay.
See you in 10 minutes.
See ya.
steeds in? Mensen nooit zeggen? Huh? Probeer.
Are you ready?
Yes.
Let's go. Let's warm up. Okay. Okay. Gents, this hydraulic criteria, I will share it to you with you now. Please, I will need you to read some of it. Kamal. Kamal. What's happening? Hello? Hello? Mama? Mama? I don't know what's happening. Hello? Hello?
Yeah, I can hear you, Said.
Yeah, okay. Let me share my
Now
screen.
I can hear you.
Okay. Kamal?
Yeah, I can hear you now.
Okay, you will take the first two. You can see
I
my
think
screen, right?
I think not now.
Okay, gents, can you see my
Just
screen?
only a black screen actually. Now I can see the WhatsApp page. Yeah.
Yes. Kamal, your tasks will be compared between these two guidelines.
Okay.
Andre,
Yes.
you will take 2 minutes, 30 minutes from your time to to compare between E and I criteria and the line size criteria. Shelly, are you here?
Yeah, I'm here.
The last two for you. Okay?
Now or
No, not
after
now.
the
Not
training?
now.
Okay.
It is just for your reading. Just this course is
Oh,
Okay.
just I want you to read it. This will give you a lot about how it's work.
Okay.
Okay. Let me now. We covering the downstream side. Let's go to the safety side. How we can support the fire fighting or the safety department as a process engineer. Typically, here is your plant layout, and here is your firefighting tank. It is a helicopter view, gents. Okay? Then we have
Okay.
one of the pumps. Then we have, typically for a firefighting system, you have jockey pump. Then we have a diesel pump. Then we have an electrical, then diesel, not diesel first. Electrical first, then diesel. Typically, gents, this network is distributed all over the plant with the different headers. Right, Kamal?
Right.
Okay. Typically, in a hydraulic, if you manage to have the pressure in the farthest way, the long distance, if you manage to have a pressure here at this area according to what you need. For example, I need a pressure here 6 bar G, so I have to make the pass, all the pass from all this way, all these branches. The delta B is equivalent between, for example, this pump will giving you 10 bar G, so the maximum delta B I can reach at this pass is 3 bar G. What I am trying to say, Kamal, is in a hydraulic, if this one is the longest pass, the longest isometrics you have on the plant, this is the farthest from the source of pressure, which is the pump. If you manage to have a 6 bar here by making this delta B, making this diameter, let's say 8 inch, 4 inch, depending on the length. If this 6 bar, that means the shortest one will be 6.5. That means the shortest one will be like 7 bar. This will mean the same 6.5. You got the point, Kamal? As
Yeah.
long as you coming closer to the pump, you achieving higher pressure. So in a hydraulic, to support them, what we are trying to do, we always asking the piping people, giving me the farthest, the longest, farthest fire header, fire hydrant. Gents, there's a lot of back noise there, wallah. Can you just...
Sorry,
Yeah,
so
sorry.
I can close my.
Yes. We ask them, can you give us the farthest distance, the longest distance, the longest isometrics until we reach the fire hydrant. Then here is the PN. Let's make another color. Here is the PN. Here is the P out. I know the distance all this way. I know the isometrics. Then I'm using the Excel sheet or using my HISIS simulations to calculate the diameter. Based on what? Based on the delta B, based on the length of the isometric which we have. That was the basis of what we are doing here. Is it familiar with, did any one of you making a water hydraulic calculation before? Did any one of you supporting the firefighting team? Let's make one now. Just make one and see how it's work. This will help us to understand how it's work. We will put some isometrics, we will put the pump, then we will ask the HISIS to calculate everything for us. Okay, gents?
Okay, Saeed.
Okay.
Let's open the devices and see. Here's the materials, the pressure drop, line sizing, okay, thickness, relation, equations, bonus equations, friction losses. Okay, pressure drop, line sizing, sizing. Okay. Hydraulic what's hydraulic process? Come on. Okay. Available liquid. Just let's ignore this one and make another one. F4 to bring all these tools, the plates. Let's define it. I don't have a water here. 1 minute, because it is all the case for me. I didn't have a water as a component for the ices. It's too old. That's why I'm going to edit it again. Then back into my simulation. As you can see, the ice is very fast. Let's go for the composition. Define it is a water stream. I will use one as a mole fraction for the water. We'll say it's okay. Then I'm asking this one to have what is the temperature of the firefighting water? 35 ambient temperature. What is the pressure out of the pump? It will be 10. Let's say it is 1 bar G. What I am trying to do now, I am trying to simulate the whole network. Why? It will help me. Bar G. Where is bar G? It will help me to simulate the whole process. How many barrels or how many liters we need for this? Let's say we are going to use 1000 barrels per day for water. Here we are. We have the defined stream. So this is the water coming from the city, from the government. It is coming with ambient conditions, coming with almost a pressure more enough just to enter the tank, our firefighting tank. Then we have the tank capacity is like 1000 barrels per day. Is it good? Does it make sense? Are you following me, please?
Yes, Saeed.
Yes.
Now I'm going to use the tank. Then with my small finger I'm going to attach it. Then this water tank typically don't have any vapors, so if you press it here you will see it is 0, but for HYSYS to solve you need to show this, so I will make a hide for it, hide only in case, just to demonstrate that here is the water tank. Here is the water tank. Now this water tank is typically have a pump, jockey pump, or diesel pump, electrical pump. Let's see one pump. I just bring one pump. To do what, sir? To take this suction from the tank and put it in the network, right?
Right.
And here is the power of the pump. What is the pressure of this pump should deliver? Let's say it is 10 bar G, as we said. So, the good part and the bad part of the HISIS. The good part, the pump is already solved and the HISIS can give you a lot of things. And that is the basis of what we are doing. Let me just delete this one. Here is what we are doing. Now, we was assuming that here is the pump and here is the network. So, we asking the piping people, please give us the isometric to do this one. So, previously we see one of the isometrics which we have, right? Let's take it and install it here in HISIS. Okay. Let's start to learn how to read this isometrics. Continue on sheet 2. Gents, please make mute. Make mute, please. Here is our starting point, coming from here, then moving all this way from the valve, going back. This line is 8-inch distance, this valve, then we have a reducer, then we have 229 millimeter moving, then we have elbow, this 135 angle, then we, sorry 45 angle, then we have 327 millimeter, then we have a tie in out, then we have another 1894 meter, and then we have another elbow, then we have 4018 or 5507 the whole distance, then we have an elbow, then we have 6638 another elbow, and keep going all this way. Now it's going underground, so we have elbow 90 going underground for 1 meter and a half, almost 1.6 meter. Then it's moving like 5 meters. It is root crossing. Then we have another 1.6 meter before going and continue on sheet number 2. Okay, gents. Hello.
Okay.
Let's see
Okay,
now
sorry.
how we're going to simulate this one. You see this pipe segment? You see this pipe segment? That's typically what we are doing in a hydraulic. This pipe segment, I don't know the diameter of it. So, I'm going to assume a diameter. First, I'm going to install the length of it. What is the inlet? Let me close it. I have 4 to inlet it, to enter it, right? Then we have something which will go to the fire hydrant. Then we have some energy stream for heat transfer and everything. Let's double click and see how it's works. What is the pipe name? It is fire fighting network. I have feed coming 4, 5 out. It said to you no segment added. Let's open the parameters, calculations, connections. Here we have everything. The method you are using, HISIS method. If you want to use another, all these are different scientists who make different colorations to calculate the delta B. All the same, yes. Some people love HISIS like me. Some people like gas and Smiler because they have a more conservative way. Let's stick with the HISIS now. Then we go to the rating. From the rating, we will find size and heat transfer. Let's go down here. A bend segment. What is segment? Segment is the section of the pipeline which we have like here. For example, this is a segment. This is a segment. The elbow itself is a segment. The line up is a segment. The elbow is a segment. And keep going. So, let's say our pipeline was straight for, let's say, 5 meter. 5 and choose the way meter. Then, is it going down or up? No. So, 0 elevation change. Let's make a trial that this pipeline is 6 inch. 6 inch, and we will see the original velocity and we will see the fluid velocity. If they are matching, then we are going to increase this 6 inch. Let's say, double click here on this one. It will open to you all the classes of the schedule. Anyone using piping before, you know that there is a schedule for the piping. Schedule 40, schedule 80 is the most famous one. Let's start with schedule 40. In schedule 40, we are going to use a diameter of 6 inch here. Automatically, we bring the nominal diameter 6 inch. Automatically brings the inner diameter. I'm telling you it is a mild steel, it is a carbon steel, or it is a rubber one. If you're using your PVC as a material, you're going to use a rubber hose. What is the difference? Mild steel will give you a roughness. How rough? The internal diameter. How rough is the internal diameter from inside? Why is this different for us? Because if this is a pipeline, typically have some roughness here. This roughness will cause a friction losses to any fluid passing through the pipeline. You got it, gents? Hello?
Yes.
Okay. So, some people, when they are designing the fire network, if we are designing the upstream piping, we are going to a mild steel. By default, it brings the roughness. By default, it brings the pipe wall conductivity, the K values, how much heat it absorbs or generate. Okay. Some people can use it smooth, which you don't have any friction losses if you are using rubber or PVC tubes. Let's stick with the mild steel. Let's close it. So This is the first pipe segment. This another one. It was a pipe. No, it was an elbow. What is this? It is every single fitting you can see on the pipeline, starting from the angle valve, the bend, the butterfly valve, check valve, coupling union, diaphragm pump, elbow 90 degree, elbow 90 degree even standard or long one, gate valve, the pipe, the plug cook, the T as elbow or T as a branch, and water meter. If you have a turbine meters, you can put it. Every single fitting on the pipeline making extra pressure drop, and that is the problem. If you put a check valve equal, if it is a gate check valve mean it is like a flipper check valve. If it is there, it's equal to almost 2 kilometers of piping, giving the same pressure drop as a 2.5 kilometer of a piping. Wow, it is amazing. So let's spot it. Check valve. Let's assume we have a check valve like swing. Let's see. Where is it? When you build the check valve, you have to define the diameter. It will be the same diameter as the pipeline, 6 inch. Then let's add another appendix. Let's see, we have an elbow 90 standard. It is like 6 inch also, right gents? All of the pipeline we are assuming to be 6 inch. All the same materials, all the same roughness, all the same pipe conductivity. How many elbows we have? Let's say we have 10 elbows across the pipeline, across the whole isometrics. So we can install 9 additional 9 elbow, or just we can type it here 10. It's kind of easy way in ISIS. We have another control valve. Let's put yes,
Alright,
that,
so I'm sorry to cut you in the increment.
yeah.
What is supposed to the increment? What is it supposed to represent?
Well, increment.
Yeah, what is it?
It is increment is just the way of calculating how many points you want the HISIS to calculate across this segment. If you put 1 meter here, for example, it will be 5. It will take 5 points to calculate the pressure drop across it. If you put it 5 meter, it will take all but again 5 meter. You can increase it to be 100. No problem. By the way, it is the default number from the HISIS to how many points you will see on the chart by the end of the day. How many points you want to see the delta B across it. You will see at the end. Don't worry. Then we have a diaphragm valve. Then we have a pipeline which is going down. If we have a pipeline which is going down like 2 meters down, we have to say in elevation change -2 to help HISIS understand that this pipeline is going down. Then double click again, going back to schedule 40, asking it is 6 inch, close it, then we have all this. So let's say that we already built the pipe class. We finished the pipe. No more to add here. No more to add here. He's saying that fitting data incomplete. Which fitting? Yeah, we missed this one. So we say it is also 6 inch. Then he asking us heat transfer information under specified. So let's go to the heat transfer. We have almost 4 techniques. Let's go to the estimate heat transfer. Why? Because estimate heat transfer helping you or asking the HISIS to calculate the actual heat transfer rate from the pipe to outside or from outside to the pipe. How? What is the ambient temperature? Let's say it is 40. Do you want to include the pipe wall in the heat transfer? Yes. Do you have any one of these? What is this? Prophase? What's prophase? What is urethane foam? Prophase, let's one by one. Prophase and HTFS and beta VUCA, all these are ways of calculating the inner heat transfer coefficients. Heat transfer coefficient. Is it important for us? Yes. It is very important if you're working in a petrochemical plant. Why? Because changing in the temperature of the petrochemical products can change it from phase to phase. But in water, you can include it. Yes, you can include it, but it will not making any difference. Is this line insulated? Yes, it is insulated. Then give me the thickness of the insulation. What kind of insulation you have? If you say no insulation, if you say polystyrene, no, I love the polyurethane. Where is the polyurethane? I can't find it. Okay, urethane foam, and then we give it thickness of it, like 10 meter or 10 feet, or what's 10 meter? It is 10 centimeter. For example, we're covering this pipeline with this layer of urethane foam. It is thickness like 10 centimeter. Then we should include it? Yes, we should. Include outer heat transfer coefficient. Why not? Is it on the ground or in the water, or it is exposed to air? It is on the ground. What kind of the ground you have? Is it sandy? Is it clay? Is it moisture sand? Let's say we are building this plant in dry sand, Saudi Arabia, for example. Then it is oak, and we have burning depths 1 meter, which is more than enough. All the information being okay, and now let's close this one. Let's see. What is the pressure here? I will show table to see. What's the pressure before? What's the pressure after? What happened? The pressure here was 149, 145. The pressure here is 1467, almost 148. Is it going high? Is it increasing? Yes. How come? This is totally stupid. Pressure drop never increase. Right, gents? Hello? Are you following me?
Yeah. Yes. It
Did
must
you-
be not
Yeah.
increase, must be decrease, I think.
Yes, totally right. But we are making one thing on purpose. What is the one thing on purpose? We're saying that all the line see the elevation change. All the line are on zero level, so it's not going
I
up.
understand.
Then it's going down for 2 meters.
We are gaining some pressure from the elevation rate.
Exactly, sir. Now let's say it is 2 meters up. Let's see. You see what happened here?
Yeah.
You got it?
Yes.
Yeah.
Hello? All of you got this? What
Yes.
I'm trying to say? This is the delta
Yeah.
B across the pipeline. Is it good or bad? Let's see. Compare with what we have for a few minutes. Let's go for the flow assurance tab. And let's start to see. Let's see the erosion here. According to API 14E, do you remember the API 14E which we say, is this a continuous flow? Is this non-continuous? It is a batch process? What? Let's say it is a continuous surfaces. The C for the equation. Do you remember the equation? C divided by the square root of rho GH. Then C100, can we put it higher? Yes. We will ask him to do hydraulic calculations, do erosion calculations. So the fluid velocity is here, almost 0.325. Yes, 3 feet per square. You have an erosion velocity here? No. Why no? Let's see. Let's see the table. He cannot solve the erosion velocity here. Why? Because already the velocity is very low, 0.3 feet per second. But I want to see how the erosion velocity will appear. So I will go back, make the diameter of the pipeline not 6 inch, I'll make it 1 inch. I will try to make a choke to the pipeline. You got my point, gents? Hello? Yes.
Yeah.
When
Yes.
when I change it from 6 to 1 inch, the pressure even is not able to reach all the way down. You get it? So if I start with 1 inch, it will not help. So let's go for 2 inch. Still not able to solve. Let's go for 3 inch. Sorry. Not able to solve. Let's go for 4 inch. Supposed to solve now. Still not solving. Wow. Let's go for 5 inch. I think it's now the HICE is hanging. Here is the problem of the student version. 1 minute. I'll close it and open it again because it is hanging. See, Andy, this when you're using a student version. And see, 5 inches is solving. Let's see, 4 inches. Sorry, 5. Let's change it to be like 3 inches. Let's see how it's working or not. How much delta B it's making? Not making a big effect if it is 3 inches. Let's go for 2 inches. I am trying to shocking the flow itself to see how it will suffer, which limit is accepting. That's why I'm keeping trying and error every time. Let's see, 140, not a big difference. Let's go for 1 inch. Expecting it again. Now we have a good pressure drop. Can you see, gents? 145, 113. Let's see. Is it working from the flow assurance perspective? We have hydraulic calculations. Erosion calculation, still don't have it. The pressure drop is increasing. Okay, let's go back. Why I'm still going down? Because I want you to see how pressure drop affecting the erosion velocity. Okay, why it is making it hard for me? From the beginning, why you are making it hard? Okay, let's do. Okay, let's make it 1 minute because it refused to be a good time. Why I'm doing that? To make it sure that we have some gases inside it here. Okay, makes sense. Here we are. The velocity of our profile. I make it 100 meter, then after the 100 meter, the velocity, as you can see, is going up all the way because it's trying to building up the pressure till it reaches the end of the pipeline. We cannot see the erosion velocity because we don't have a mixture phase. It's going to stay zero. Then we have the hydrate formation. If you want, I do hydrate formation curve, as you can see from here till we reach the full distance. Then we can make a slag flow if you want to see how many slugs you are participating or expecting for the liquids. Then for the oil, we have the wax formations. Here we don't have any wax, so because we don't have oil, we have only water. That's how the hydraulic works, gents. You get my point, gents? Questions, please. Ask me. Hello, Houston.
So why wasn't there any? Why didn't you even calculate erosional velocity?
Because erosion velocity here is very low. When he calculated, it's going to give you 0. Let's change it. By the end of the day, you are very far from the erosion velocity. Don't have a fixed phase here. Let me put it in this way. It will be helping you to see it. 1 minute. Oh, I'll start to hit this. ISIS is hanging. Typically, when we have. Okay. Why not solve it? As you can see, gents, I even
Yes.
bought a 1 meter piping, and it's not solving, because typically the height is hanging when you're using this student versions. Let's plot it on Excel sheets, which should be easier for us. Let's close it for the last time before we go for Excel sheets. This over on the other side, Excel sheets. Missing. Okay. Gents. Hello?
Yes.
What we was trying to do is city water coming for firefighting tanks with a 1,000 barrel capacity per day. Then we're using the pump to put it in our network here. On the network we are producing the fire hydrant with a pressure almost close or above to the 6 bar G. We play with the diameter here as much as we can to keep it from 6 inch till almost half inch or 0.8 inch at the end. Why you are doing that? To make sure that we have the minimum diameter which is able to achieve the 6 bar at the farthest point. Why you don't have original velocities here calculation? Because it is a cracked version, not the full license version. It is the student one. Typically we should have the erosions numbers here to have another line crossing this way, but obviously it is the correct one or not working like this. Anyhow, the most important part for me. Now we understand how we can change the diameters, how we can play with the diameters here to get the end result of what we need about the pressure at the hydrant. This kind of things we are providing to the firefighting people. That kind of things we are providing to the loss prevention engineers to help them in sizing the water hydraulics. Okay, Jets. Hello.
Yeah.
Is it clear?
Yes.
I have one problem. The mechanical people, the rotating engineers, they will ask us about the pump data sheet. The pump data sheet. How it's been created, how it's been working, what is the net positive suction head for this pump. Before we jump to the data sheet, let's discuss some points. What is the meaning of net positive suction head? Gents, this is a question for all of you. Hello? Houston?
Yeah, I'm listening.
Yeah.
Sayed.
Kamal, I miss your voice.
I'm listening to you.
Okay. Andre? Philly?
Yeah, I'm still here.
Yes? Start to speak. What is net
You're
positive
talking about
suction
the
head?
net positive suction head.
Yes, sir.
Yeah, the practically the height that the pump can deliver in terms of the maximum height achievable by the pump when it starts
Yes.
pumping the fluid. Yeah.
This is what you say is the differential pressure for the pump.
No, I'm talking about height.
Yes.
Like
When we saying this pump is 80 meter,
yeah.
this means the differential pressure of the pump. This means if you enter it, this 80 meter is almost equal to 7.5 bar G. This means if you enter a section of 1 bar G, it will deliver to you 8.5 bar G. Let me put it another way. Andre, are you here?
Yes, I'm here.
Now your operator coming complaining to you. Mr. Andre, please, the pump was every time it is cavitating now. This pump was working like for 10 years in a perfect conditions, and there is a separator in the top of it. It taking the liquid level, 50% of the separator, and the pump now is cavitating after 10 years of good work. Now you are the process engineer for this plant. How are you going to tackle this? Tell me. Think loud so we can all listen to what you're thinking about.
I will ask him to check the isolation valves on the pump suction and liquid level in the vessel.
Kamal,
Yes.
what are you going to do? Mr. Shili, I am coming after Kamal to you. Try to think about it. The way of thinking.
It's a pressure difference.
What's the pressure
According to the
difference?
water column and the pump, I think. I can do the pump section.
Okay, Mr. Shili.
Could be the pump impellers are having problem.
One, that's good. Now you have to check the maintenance record, and you'll find that these maintenance records are being achieved across the whole 10 years. The maintenance people are doing great in keeping the maintenance record. The man who is typing on the computer, try to think here, please. Who's typing on the computer? Kamal, you're the one who's typing on the computer, right?
Yeah.
Are you in the work?
Yes.
Ah, that's why. Okay. Tell me what we're going to do. Let's focus here, Kamal, I will tell you. First of all, we have to check the maintenance record.
Yes.
Now, if we are working as a process engineer in a running plant, from the maintenance record, we will understand what is the maintenance frequency of this pump. Is it having any deficiency problem? That's first. Second, we will start to ask for the trends. Do you know trends? The level trend. How much level here when this pump is running? How much here when the pump is running? I will ask for the whole months, the previous months. That level is fixed or it's going up and down. Third, I will ask for the vapor pressure, the pressure of the separator. Is it changed the whole last months? Yes or no? Occasions. Also, Andrew, I will ask for the isolation valves. Does it make sense, gents?
Yeah.
All the four, I found them very perfect, 100% efficiency. 100%. They are fixed, steady state, not changing from the first day of operation. Then I will start to ask about the net positive suction head. The net positive suction head. What is the net positive suction head?
It's the pressure difference between the pump suction side and the water column.
No, I don't love this. I don't love this definition. Let me put it this way. I am not a man who memorized the equation in himself in his mind. So I try to bring it every time. Typically, what pushes the liquid here to go all the way down till the pump suction? Tell me. What push the liquid here all the way down to the pump section? We have some pressure here, gas pressure, right?
Yeah.
Yeah.
So pressure. What else? The weight of the liquid, right?
Yeah.
Yeah.
Which weight till the center of the pump plus rho GH, right?
Yeah.
What prevent the liquid from going down? The friction losses inside this pipeline, right, sir?
Yeah.
Yes.
Delta P in the pipe of the suction. That is the equation of the net positive suction head available. And take care, because now we have available, we have net positive suction head required. We're going to see the difference between them. Available is what provided by the system configuration you design. Here is your system, and that's provide you net positive suction head, let's say 30 meter, 3 meter. After you calculating the pressure here, and you make sure it is a fixed from what we did here, the first one. The second one was the level of the liquid, which is good. Then you calculated you see the maintenance record, and make sure the isolation valve is good. the net positive suction head and the head required to keep the flow in the liquid phase until it reach the pump suction. Okay, let me put it in another way. What happened if the friction losses here was greater than the friction losses in this pipeline was greater than the plus term, the pressure and the rho GH? What will happen, sir? You will have a negative positive suction head. What is the meaning of negative positive negative pressure suction head? What is
No
mean?
flow to
That's
the pump.
that's mean the liquid here in this line will not have pressure on it, gas pressure on it, to keep it on the liquid phase. So this liquid will start to vaporize, not totally vaporize, to like 10% vaporization, 20% vaporization. And that what will happen when it enters the impeller of the pump.
It goes to cavitation.
Yes,
guess.
sir. It will making here, coming here. It will cause you the cavitations, and it will making the deficiency of the pump, the power of the pump, the differential pressure of the pump. If it should supposed to deliver 8.5, it will deliver like 6, will deliver like 5, and you will have a high vibration. Why we have a high vibration? Because we have the impeller here. It is moving in the liquid, then in the gas. When it reaches the gas, there is no resistance. In the liquid, there is a resistance. So in the gas, the impeller velocity increase a little bit compared with liquid. Then it's hit the liquid again. Then the velocity reduced again. So the velocity of the impeller will be like moving, then up, then back down, then up again, and keep going. That behavior makes the vibration of the pump. Make the vibration of the pump. So, basically, what we are trying to say that you have to check the net positive suction head available from the system. You have to check it what is available of the system. So, in the case which I was saying, this pipeline was replaced after measuring the pressure here at this point and measuring the pressure here at this point, and we find the delta P was high. That's indication of the piping internal friction was increased very high due to the presence of water. There was the corrosion mechanism and this piping, and that was making a high friction losses. So after replacing this pipeline, the pump working perfectly again for additional 5 years. You got it, gents?
Yes.
Any questions? Hello?
Yes.
Tell me, any questions?
Not from this side.
Okay, other sides?
No questions from me.
Okay. Today we will take a break for 1 hour for me to doing my praying. We will back after now in my time it is almost 10. We will back at 11 o'clock sharp. Okay, gents?
Okay.
You almost have like 1 hour 10 minutes for break.
Okay.
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 When we come back, we will making the required deposit suction head, and we will making the data sheet, and we will bring it out from the HYSYS. Okay?
Oh, okay.
Okay. Enjoy your break.
Yeah. See you in 1 hour.
See ya. Bye.
See you.